You'll notice that this is 2.0. I gave the same presentation last year. I had a few parts at the end that we didn't have time for, and we probably won't have time for this time as well. So I made some changes to it and included move semantics, which hopefully we'll get to. I'll try to blaze through this. But if we don't, you can always go back to the slides. Just be aware that if you reference the last slides, then the last few parts, raw pointers and templates, those are they're written to help like understand the concept and make it natural. But the code that I write to help make it natural is not code you would actually want to commit to Chrome. It's sort of oddball code just to understand it. Okay, so let's go ahead and begin. This is the roadmap we're going to be talking about. I'll just sort of glance over it for now. And we'll start with free functions. So the code here is Java. I'm going to be picking on Java a lot just because it's easy for everybody to sort of glance at and understand, even if you're coming from Python or whatever. But Java is a purely object-oriented language. And as a result, you'll see that first bit of code has class hello world app, and then there's a function. It's the entry point, the main function. And we had to mark it static. So this is this oddity of Java that we never got a chance to instantiate this class because we are just now entering the program. And we had to mark this function as static as a result because we couldn't instantiate it. And on top of that, this could have been in any class. It didn't actually have to be in the Hello World app. It could have been in any class at all. So the main function is really not associated with a given class. And we kind of have to break pure object orientation to get this entry point. So it's kind of weird behavior, but that's how it is. And same with below that, you'll see this class java.lang.math. Well, really, that's a namespace. We're not using the class. We're getting the maximum of 2 integers, and we don't need it to participate in any sort of class or object-oriented, any of that stuff. So in C++, we wouldn't have used that. They would have been what's called free functions, meaning they're not associated with a class. The top is the entry point. It's just a regular old function. And below that is the max, regular old function, no classes at all. So include and linkage. I have pairs here. You can see at the bottom, the C++ section, the first include uses angle brackets, and then the second include uses quotes. If you include with angle brackets, that's more like you're trying to fetch a file that's from some library that you downloaded. If you use quotes, it's supposed to be like this is our code in our project. The reason you do that is you can actually specify different search paths for the different types of inclusion. So you can say, if it's a library, I want you to search these directories, but if it's our code, search these directories. And that kind of pairs up with the Java and the Python examples. It's kind of like if you're importing a system library versus importing your own code, stuff like that. So the way C++ is compiled is each separate code file is compiled independent of each other. So you can see a.cpp is passed to a compiler and b.cpp is passed to a compiler. They're completely unaware of each other. Those each output an object file, and then we gather up all of the object files and send those over to a linker, and the linker will then make this program. So this kind of results in there being a compile phase and a link phase. Now this isn't 100% true, but it's mostly true. And the reason why is the compiler could actually pass extra info over to the linker, and the linker can generate code. So that's called link time optimization. So there are kind of exceptions to the rule always. But for the most part, we can think of a compile phase and a link phase. So because these files are compiled completely separate from each other, we need to have some way to explicitly say, I do want to export this function and make it visible to others, but I don't want to export these other functions. If you just go with the defaults, it gets a little bit messy. There could be some sort of collision, like if you have 2 functions with the same name. The linker will not know what to do with that. It's not supposed to happen. And so sometimes it'll just choose one, and it can be kind of risky. So you want to be kind of explicit about, these functions get exported, these ones don't. So here I have two separate ways of marking a function as don't export this. The first one is using an anonymous namespace. That is what we prefer in Chrome, and that's kind of the new style. The one below that, the bottom line, is marking it as static. That's kind of the old style. It still works, they're the exact same, but I think nowadays we prefer the anonymous namespace. So that's if you don't want to export a function. But what if you do? Typically we have several code files because we want to organize them well, and then code from this file needs to be calling code from that file. So we do want to export stuff. So in C++, the way we typically do that is we make a pair of files. On this slide, you see I have computeharmony.cpp, that's my code file, and then I'm going to pair it with a computeharmony.h file. That's the header file, and typically in the header we include all the stuff that we want to export and make visible to other code. So here's an example of that. At the top we have computeharmony.h, our header file, and we're going to make a forward declaration that there's going to be a function named computeharmony. It takes no parameters and it returns a void. Then in computeharmony.cpp, we include our computeharmony.h, and we actually implement that exact same function. The reason you include it is to sort of provide yourself a layer of protection that does my function match the declaration that I said I will be exporting. And then below that, we have other.cpp. And you see it also will include computeharmony.h. And in the code, it's trying to call the computeharmony function. Now remember, this is two separate files where the function here and then function there, and it's calling over. What's going to happen is at the link phase, at the compile phase, it knows it's calling a function. It knows what the signature looks like, so it knows how it should be calling it. It just doesn't know the address of the function it's going to be calling. So at the link phase, it says, oh, I'll go ahead and connect that dot for you. So our graph kind of updates like this, where we have a.cpp and a.h. We kind of get these inclusions that span the separate compute lines. Oh, I should explain, by the way, a.cpp and b.cpp go into separate compilers. We call those a translation unit. So when you're building a project, you have multiple translation units, and each one only has visibility to what it sees. Okay, so these includes, all they're doing is opening that file and copying and pasting it onto the include line. So it's replacing the include with the actual file contents. And that's going to lead to an interesting problem. So here at the top, we have musictype.h. It's a header file. And instead of just forward declaring that there's going to be a class called musictype, we're actually providing the musictype body, the actual class itself. So it's not a declaration, it's a definition. And then below that, we have jazz.h. It includes musictype.h. And we have class jazz, which derives from class musictype. That's why we had to actually specify the class body, not just a forward declaration. If we're going to derive from it, we need to know what it looks like. So below that, we have classical.h. It's going to be similar to jazz.h, where it'll include musictype.h and it'll derive from it. And then at the very bottom, we have this playmusic.cpp. That's going to include both jazz.h and classical.h. And as a result, we kind of make this like diamond shape where we've included these two files, but they both include that file. And now we have multiple definitions of this class music type. That's a problem. You're not allowed to have multiple definitions. So this is me talking about those multiple definitions. Here's how we fix it in C++. If my file name is musictype.h, then I will start off with this pound if not defined, and then all capitals musictype_h. And then right after that, I go ahead and define it. So if it isn't defined yet, define it now. And then we include all of our normal code, and then we end the file with this pound end if. What that does is the first time the file gets included, musictype_h hasn't been defined yet. And so we go ahead and include all of the code. And then the second time it has been defined, and so we don't include any of the code. This way you can include the same file multiple times and it's not going to be a problem. There's other ways we could do this. You can use pragma. There's this pragma once. Most modern compilers support that, but it isn't standard C++. So I'm just mentioning it as an option, but it's not what we want. Okay, destructors and scope. So let's say I have a class in Java that represents like a file or a network connection or something along those lines, database, something like that. It represents a resource. Java is a garbage collected language. So when I lose my final reference to this resource, I don't actually know if it's going to be cleaned up yet. The garbage collector might come 5 minutes from now. It might never come. We don't know that. So if I have override of the finalize function so that it can do all the cleanup, it may never actually get cleaned up. So representing a resource in Java is actually pretty difficult. As a result, we typically will add a .close function so that we can explicitly terminate this thing. But if you're a programmer, what if you forget to call .close? It's kind of not a beautiful scenario. C# added the using keyword. So you can say using this variable and then provide a scope. And inside that scope, or once you get to the end of the scope, the garbage collector is guaranteed to come and look at that variable. Java did the exact same thing with automatic resource management. So this is good. Now we have some form of saying like, I know the finalize function is going to get called or the destructor is going to get called, and I know when it's going to happen. But that still puts the burden on us, the programmers using it, to remember to use the keyword or to call .close. It's the exact same problem. If I forgot to call .close, I'll forget to call using. We haven't really solved the issue. So what we really want is deterministic destruction, and that's what C++ has. Here's an example of a class, and inside it we have this function that starts with that tilde, and then it's the class name. That will be called whenever your object goes out of scope, and it happens right then and there. It's deterministic when it happens. So as an example, here we have this function doThing at the bottom. We create a destructor example named cleaner, and at that closing curly brace, that is where the destructor is going to get called. In fact, you can insert scopes wherever you want. So here we call do first thing, and then we have a scope so that the destructor gets called before we do the second part. And this is really good if you're trying to represent resources, like I said, a network or a file or a GPU or something like that. If it's an actual resource, then you want to have a way to represent it safely, and deterministic destruction gives that to us, which ties in closely to RAII. RAII stands for Resource Acquisition is Initialization. And to give a rough idea, this is old style C++. Don't write this code. But what we do is we'd have some resource, say GPU. We allocate it in that first line, and then we call .open to actually initialize it. So for example, here, we're going to initialize it using the default GPU. Maybe some systems have multiple GPUs. And then we have to check if the initialization failed. So this is the opposite of RAII, where the resource hasn't been initialized when we acquire it, and we actually have to have a separate initialization step. And as a result, the object itself has to keep a state of like, have I successfully initialized? And then all the functions you call will have to check that state. Have we been initialized or not? We don't want that. That's completely overhead. It makes the code hard to read. It's kind of a mess. So the alternatives are, if you know the initialization will always succeed, then you make a what's it called? A factory, which is this top function, and it will always just return the thing you're trying to initialize. But the second piece of code, if it might fail, then we can use base optional. That class is either the thing you want, which is a GPU in this case, or it's nothing. So if the initialization failed, if it's maybe going to succeed, then we'll return this type that represents maybe success. The benefit of doing all this is now the type GPU doesn't need to know whether it failed or not. You don't have to have every single member function checking if we've initialized. And we can have this like very clean abstraction of like, if I have a GPU, it's working, it's doing exactly what it should do. There's no second auxiliary meaning to this class. Additionally, I mentioned this base optional is either the GPU you want or nothing. Maybe what we want is the GPU or an error code why it couldn't initialize. So you can make something like a pair or something like that to represent why it couldn't initialize. Or you could have an out parameter that's the error code, something like that. But just be aware of the idea of separating initialization and the resource itself. Okay, pass by reference and value. So if you're used to Java, looking at this function add to dictionary, it takes in a parameter word. This is normal. What's actually happening is a reference to a word is being passed into your function. But if I read that exact same syntax from a C++ standpoint, it's not giving me a reference. It's actually going to make a copy of the word that gets passed in. And then that copy is what I get to use inside the function. So that means if I make changes to my copy, the outside caller won't see those changes. This is called pass by value. If I want to allow somebody to make changes, then I can add an ampersand after the type. Now it's an actual reference. This is pass by reference, coincidentally. But I want to point out, even though I'm using the word reference, that does not imply reference counting or any sort of garbage collection or memory safety. It's basically just a pointer, and you do not gain any safety because it's a reference. So what if I want to pass a reference and avoid this expensive copy, but I don't want to allow somebody to modify it? Well, then you can throw the const keyword on there. This is what you will typically see. But I should point out, I said a reference is a pointer. That implies some indirection, that I have this value, now I have to go follow that value in memory. It's extra work. So if my type is actually really, really cheap to copy, like say it's an integer, I'd rather just pass in the integer and make a copy. But if it's an expensive type, like maybe some complicated class, then a const reference is probably the better option. So here's those three examples and when you would use each. So the top one is if we're just observing the value, then take it as a const reference. If we must modify it, for example, if somebody's giving us an array and saying, can you please initialize my array, then take it as a reference. And the last one is if it's cheap to copy, like an integer, or we're possibly taking ownership. The end of this presentation, if I have time, I'm going to talk about move semantics. But move semantics basically is the idea of passing ownership around. And if we might be taking ownership, like somebody says, I'm done with this, I want you to take it from now on, and I'm never going to touch it again, that's when we would also use the pass by value. Okay, the standard library. C++ is unfortunately lacking in the standard library. Java's standard library is astronomically large. C++ is big, but it's nothing compared to Java or Python or almost any other programming language. For example, Java has sockets and networks and all this stuff. I think there's even like GUI code in there. We have none of that in C++. We're getting sockets soon, maybe, who knows. But yeah, the typical solution is we go find a library that is well accepted, that everybody likes, and we use that and include it. So C++ projects typically have many more libraries than most other languages. From the standard library, there's three parts I want to point out. They're going to be the most useful. That's a string, a vector, and smart pointers. So to include string, you just angle brackets again, and the file name is string. Same with vector. And then you would use this std : string. That is standards namespace. So it's standard string. And then, of course, dog name equals Fido. Vector is like an array, but it's dynamically resizable. So if we need the array to grow or shrink, we can do all that. So here I have a standard vector of integers with values 1 through 5. And then you can actually combine these. So below I have standard vector of standard string. And now I can have a vector of multiple strings. So what I just showed you, those string and vector, those are standard containers. Smart pointers are also going to be standard containers. But there's a piece of the standard called standard algorithms. And it's really useful, and we almost never use it. And I think that's many C++ programmers, if we went to like a class, we were asked, write bubble sort or something like that. And as a result, we end up writing these functions ourselves, and we kind of ingrained that behavior. That's my guess as to why we don't use these standard algorithms. But we should be using them more. So there's standard sort, there's standard copy if. So if I have two vectors, I can say copy from vector 1 into vector 2 only if the value passes a predicate. Like maybe my predicate is the value greater than 10 and less than 100. If the predicate passes, then copy the value. So there's all these amazing things that we end up writing ourselves. We shouldn't be doing it. We should be using the standard algorithms. And if you do it, other C++ programmers are going to be like, oh, this person's really smart. So look good, do it. Okay, smart pointers. How are you doing on time? Ooh, okay. So last time I gave this presentation, I asked the room to like show of hands if you've heard horror stories about C++ and pointers. And the entire room raised their hand. I'm pretty sure even the person operating the camera and the soundboard raised their hand. Like, it was bonkers. So I'm going to present smart pointers, which gets rid of all of that. It's not scary at all. And it's actually very similar to what you're probably used to. So if you're coming from a garbage collected language where things are reference counted and so long as there's one reference, the object will stay alive. Here we have standard shared pointer. It does the exact same thing. The ownership of this thing is shared amongst everybody holding a reference. And when the final reference disappears, that's when the thing itself gets destroyed. So this is very similar to what you're used to in a garbage collected language. But there's something I want to point out. Shared ownership like that is actually very strange. We rarely would say, like, I own my car and my roommate owns my car. That's not really how it works. You typically, like, one person owns the thing. So in C++, we don't want to use shared pointers that much. It would be easy to say, like, oh, just shared pointer everywhere and be done with it. But that's actually not what we want. What we want is to have a very clear lifetime. This is where the thing is created. This is where the thing is destroyed. And its lifetime is tied to some other object that owns it, something like that. So to represent ownership in a better way, there's this smart pointer called standard unique pointer. It's unique because only one reference can exist at a time. Well, 1 or 0. So if I have the reference and I want to give it to somebody else, they can't make a copy. I have to move my ownership over to them, which is also part of the move semantics that hopefully we'll get to. But once I move ownership, I no longer have a reference. They take the reference. And yeah, I mentioned that we have to standard move the thing. We can't copy it. Okay, move semantics. So I have just a little bit of time left. I'll try to brush through this real fast. Here I have this function getName. We return a string, and then I'm calling presenter.setName with the result of getName. I'm going to gloss over return value optimization for now, but old style C++, we would see this as a code smell because it creates a temporary string, and then inside setName, we're going to copy that string, and then we destroy the temporary. And having all these temporaries that we create and destroy all the time is really expensive. So here's an example of, there's the temporary blue box, and it has a pointer to its buffer it had to allocate. And then it has all the unique characters inside its buffer. And then when we make a copy of it, we have to, inside presenter.name, we're going to allocate a new buffer and copy every single element over. And that's kind of expensive. So what if we knew that this thing was a temporary? What if we knew that it was about to be destroyed anyway, and nobody else had a reference to it, and we could modify it all we want because nobody's going to see that we modify it? That's where move semantics comes in. Instead of making a copy of the buffer, what we can do is steal its buffer and then set its pointer to null so that when it cleans up, we take ownership of it. So that's all move semantics is. And you'll learn about standard move and stuff like that later to facilitate all this stuff. It looks like that's it. Okay, thank you, everybody.